the same answer?
No.
Okay, what's the...
They'll come in close, they'll give you the same feel for what's going on, but they won't be precisely the same thing.
But they should be at least somewhat close? Or not even really? Because
Heuristically close.
that doesn't help at all, right?
They're close in the overall behavior that you're going to see. So the nature of your equilibria are going to be the same.
What, the equilibrium?
But the equilibria themselves, no.
They don't have to be.
But you'll know that the bigger one is stable and the smaller one is unstable.
Okay.
And things like that. And frequently when you're in a real life situation, that's really all you care about, because most real life situations are what we call stochastic, which means that there's some sort of random fluctuation that goes into them anyway. So nailing down the equilibrium value for the bison population in Yellowstone is really just a silly exercise. There is no single stable equilibrium value for the bison population, because every winter is different, every summer is different, and so you're going to have these random fluctuations around an equilibrium value. So what you know is that there are equilibrium values there, but you're just going to fluctuate around. And so all you need to know is that equilibrium value stable or is it unstable? And I can use the derivative to figure out if it's stable or unstable. I can use the subtract b sub t method to find out if it's stable or unstable. And in the end, that's all I really care about.
But should you get the same number of equilibrium points even?
Yes, that you will.
Okay.
So, all right. No, there might be an exception to that. Sorry. There are. Let me show you the other way, more popular, well, these days, probably most popular way, of solving these. And then I hit the wrong one. And that is to find what's known as a numerical solution to your difference equation. The ones that you've been finding phase lines for, analyzing the equilibria for, and so forth, like this one that you just did, there is no way to solve it. There's no way you could ever write down b sub t is equal to and just have a nice equation, nice little formula where you could plug in t and boom, out comes b sub t. So it's not even possible to write down the solution to that one. So instead, if we actually want numbers, we actually want to crank out specific numbers, we have to go over to a spreadsheet and let the spreadsheet do the calculations for us. And thankfully, difference equations are set up perfectly for spreadsheets, or vice versa, whichever way you want to think of it. Because here, given some starting values, starting value for b sub t, I have a formula that tells me what the next one would be. And I can just, that naturally fits into the cell structure of a spreadsheet. So up here I have t and b sub t, and I know that when t is equal to 0 I have 1, say bison, and then I have this formula for how things go as time goes on. And so I can just type this in. So I need to get the next one, I take the previous one and cube it. So I'm going to need to just type in my formula. I take the previous one and I raise it to the third power, and then I subtract 7 times the previous one squared, and then I add 9 times the previous one. So I can just take my difference equation formula, type it in, and hit enter. That's nice. And then if I come up and I just take that and drag it, it will go and calculate all of the numbers for me. Now, if you looked at it, your equilibria were at, what was it, 1.44 and 5.56 for that one.
I don't see this as the bison population. I see this as the government spends money.
Okay, that's fine. Yeah, negative bison is a little hard. Just means that the herd went extinct, so.
Big time.
Yeah. And so we go on and go through those. So we can take any difference equation, we can throw it on a spreadsheet, and we can solve it that way, solve it numerically, actually do the calculations for it. Or we can analyze it in terms of equilibria and things like that. And then if we're really lucky, which really means if it's really simple, we can actually solve it and actually find a formula that we can use to do it. But that's pretty rare. Well, pretty rare. Very rare. Any questions about using a spreadsheet? Is everybody up to speed on spreadsheets?
I have a question related.
Lisa.
We jumped from 3 to -9.
Yeah.
Did we not say 0 was... Oh, that's a going away one. How do we jump from 3 to -9?
How did we do that?
You plug it in.
First of all, we should make sure that I typed it in correctly.
I think it's just the grain of your t value.
Huh?
I think it's just
Oh,
the grain of the
jumps.
t value. Yeah.
So,
Well, it should go to 0 then. If it hits 1.4,
It should go up to.
it should have gone up to 1.4.
should have gone up to, well, it should have gone
Should've
up
gone
at least initially.
Yeah.
Well, it did go up initially.
And then it should come down.
And then what happened after I hit 3?
It came down too far.
Came down, but it came down to
That's 2 equilibriums.
far. It skipped over 2 equilibrium points and hit a -9. And once I hit -9, it just kept going. So it was, there's too much, like I say, it's the, with time steps of 1, this thing jumps too much. Jumps right over the equilibrium and landed in a different spot. Other questions? All right. Then, so this is our fallback position. You can always do a numeric simulation of whatever you're doing, if you can't get the rest of the stuff to work. Now, field trip next week. So 2 things. Next Tuesday.